So we know what the distribution of ranks should look like, and it turns out that if we randomly draw a subsample of those ranks and say they're from group 1 and add them up to get the rank sum, it's going to look approximately like a normal distribution. Let me show you that that's true. Suppose that our data set consists of only 4 units. Then on the left we have a histogram of the numbers from 1 to 4. 1 appears once, 2 appears once, 3 appears once, and 4 appears once. Then if I were to write down all the possible ways to add up 2 of the 4 ranks, I would get the distribution on the right. Right? Because if I add up the numbers 1 and 2, I get 3. If I add up the numbers 1 and 3, I get 4, etc. If you look at all the possible sets of 2 of the 4 numbers from 1 to 4 and add them up, you get the distribution on the right. What if I have the numbers from 1 to 6? If I have the numbers from 1 to 6, then the left-hand picture shows what a histogram of the data looks like after it's been transformed to ranks. 1 appears once, 2 appears once, etc. And on the right, what we see is what we get if we look at all possible ways to take 3 of the 2. It's starting to look more like a normal distribution. Now say we have 10 values, the numbers from 1 to 10. This is still not a big data set, right? If we have 10 values, it's still not a large data set at all. But if we now look at all the possible ways to take a subset, to take 5 of the 10 ranks and add them up when the ranks are the numbers from 1 to 10, if we went through that process, we would get the distribution on the right. The point is that for fairly small sample sizes, the reference distribution that we get for the rank sum, if we actually wrote out all the possibilities, starts to look like a normal distribution. And so what people tend to do with rank sum tests, and what many software programs do, is for any sample size that's relatively large, we just calculate the mean and the variance based on the sample sizes and then assume normality instead of going through the process of writing out every possible allocation. The central limit theorem is what we're showing here, and it's an idea that we'll come back to. But the idea is, regardless of what the population distribution looks like, and regardless of what the distribution on the left looks like, if we randomly draw samples of the values from the distribution on the left and add up the values in the sample, and we do that repeatedly, we're going to get a picture that looks like the normal distribution on the right almost all the time. Again, no matter what the picture on the left looks like, no matter what the set of values looks like when we make a histogram, if we randomly draw subsamples of that data set and add up the numbers in the subsamples, and then go back and select another sample and add up the values in that subsample, if we do that repeatedly, we're going to get something that looks like a normal distribution. And that is an idea that we will come back to.